All right, so we're going to study kinematics again, but now we're going to do it with calculus and do some more complicated problems. So let's be reminded, first of all, of the power laws for differentiation and integration. When we differentiate, the constant gets pulled out, you bring the exponent down, you reduce the exponent by 1, but then you remember the chain rule, you have to multiply by the derivative of the argument. For integration, the power law says, once again, pull the constant out. For integration, you increase the exponent by 1. But then, of course, you have a constant to add on the end if you're doing an indefinite integral. If the exponent's -1, though, then when you pull out the a, this is du over u. -1 would yield a 0 denominator here, and we don't like that, so we actually have to go through and evaluate again. It turns out, of course, to be the natural logarithm of u. And if you're picky, as we are sometimes in math, it's the natural logarithm of the absolute value of u plus a constant c. So those are the power laws we need. Now we're going to be dealing with non-constant acceleration. And in that case, none of these equations are true. Those are only true for constant acceleration equations. Okay? And our accelerations in general are not going to be constant. They'll be functions of time, position, or velocity. So, simplest case, you're probably familiar with this. Let's look at a time-dependent problem. Now remember that if you know the position, you differentiate once to get the velocity, then you differentiate again to get the acceleration. So this is a problem you probably did in Calculus 1. Here's a position function. Let's find the velocity. Well, we'll drop the vector signs because this is just one-dimensional. And we'll just differentiate this using the familiar power law. So derivative of t cubed is 3t squared. The derivative of this term, the 2 comes down and cancels, so you end up with minus 7t. The derivative of 2t is just 2, and the derivative of 1 is 0. So there's our velocity function. Our acceleration will then just be the derivative of the velocity. So we're just going to differentiate again, dv dt. And that's going to give us 6t minus 7. So we were asked to show that, and indeed we have. The next thing we're asked to show is the times when it stops. Well, we need to use a bit of physical reasoning here. Stops, of course, happens when the velocity is 0. So here's our velocity function. 3t squared minus 7t plus 2. So we're going to factor. It's going to be 3 and 1 there. This will be 2 and 1. Middle term's negative. So we can see that these will be our two terms because 3t times minus 2 and minus t together give us the correct middle term that we need. So 3t minus 1 and t minus 2. So that equals 0, you can see when t is indeed a third in the first bracket and then 2 here. So we have indeed shown what we were asked to. The maximum speed, well, you can maximize this by taking its derivative and setting it equal to 0. Or you could, I suppose, look at a graph of this function. It's got zeros at a third and 2. So it is a smiling parabola with zeros at a third and 2. So the velocity function is going to look something like this. This will be velocity as a function of time. We're asked for its maximum speed to the left, so that's the maximum negative velocity. So that's just going to be here. That will be the location of the vertex of the parabola. Notice that at that point, the acceleration is 0. So when you're at the maximum speed, you're not going to be accelerating. And that's just another idea from Calculus 1. You get a maximum when the derivative is 0. So where is the acceleration 0, i.e. where is dv dt equals 0? Well, that's going to happen when time is 7 over 6 seconds. At that time, that is when the maximum velocity to the left is going to occur. So then you need to take this 1 and 1/6 seconds and substitute it in to find the velocity at that time. So So you want to find the velocity at time 7 over 6. So that's going to be 3 times 7 over 6 squared minus 7 times 7 over 6 plus 2. And you could show that works out to minus 2.08 meters per second. All right, so that's a familiar Calculus 1 problem. Another familiar Calculus 1 problem is if you need to go in the other direction. So because, say, the acceleration is the derivative of the velocity, we can cross-multiply that. A dt is dv. And if we want to work backwards from the acceleration to the velocity, we can see that we're going to need to add up or integrate. So integrating from an initial time to a final time, this side's a velocity integral. And the integral of dv is really easy to do. It's just v. Then you've got to put in your upper and lower limits and subtract. Now, of course, this interpretation here, integral a dt, is just the area under a velocity time graph. So the area, under an acceleration time graph, tells us the velocity change delta v. Okay, in a similar way, we can cross-multiply here, and we'll get v dt equals ds. So this is a time integral, so we're integrating from an initial time to a final time. This is a position integral. We're integrating from an initial position to a final position. Integral of ds is just really easy. It's s, and then you put in the upper and lower limits. So this tells us the change of position is the integral of v dt, but of course the integral of v dt is just equal to this area here. All right, so that then is how we will work it backwards from an acceleration to a position. So for instance, here's a graph of acceleration, and there's its equation. Acceleration is a function of time. And we want to find the velocity and the position. So we start with acceleration's dv dt, and then we cross-multiply that to get dv is a dt. And then we're going to integrate. This is a velocity integral. So we're going to integrate from an initial velocity. And we're told the initial velocity, by the way, is 3 meters per second. And then we integrate up to some unknown final velocity. Now that 3 meters per second corresponds to a time of 0. So our initial time here is 0. And then we're integrating up to some unknown final time. Okay, now this side's really easy. The integral of dv is just v, but then you've got to put in the upper and lower limits and subtract. This side here, well, we can put in our acceleration function. It's just 1 plus t dt. So when we integrate that, we're going to get t squared over 2 plus t. Then we have to put in the upper and lower limits and subtract. Now there's no plus c here, of course, because we're doing a definite integral now. And so that's just t squared plus t, because the lower limit just gives nothing. Then we bring the 3 over, and then we get the velocity as a function of time. It's going to be t squared plus t plus 3, and that's what we were asked to show. Now we also want the position function. Well, we know that velocity equals ds dt. So we cross-multiply, and we get ds equals v dt. This is a position, this is a time integral. Now we notice that our initial position is 5 meters, but that's at a time of 1 second. So we're going to put in a position of 5 and a time of 1, because this is position as a function of time is 5. Our final position is unknown, and it depends on our final time. So we'll now work out this integral. Well, first of all, the left-hand side is trivial. The integral of ds is just s. Plug in the upper and lower limits, s minus s naught. You get on that side. Here we now have to substitute in the velocity function that we just came up with. It's 1 to t. It's t squared plus t minus 3, all of that dt. Now, that's going to be, well, a little bit more work here. It's going to be t cubed, let me try and squeeze it in here, t cubed over 3 plus t squared over 2 minus 3t, and then we have to put in the upper and lower limits. We've got to put in t, and we have to put in 1. Now, putting in t, okay, now that was actually plus 3, so that sign needs to be plus. So when we integrate, we get plus 3t. So you put in t, and when you put in t, you, of course, get t squared plus t. Oh, darn. Let's try that again. So after you integrate it, it's t cubed over 3 plus t squared over 2 plus 3t. Then you got to subtract, and then you need to put in 1 here. So it's a third plus a half plus 3. So that's 3 and 5/6, which is 23 over 6. So then you bring 5 over to the other side and add. And you get t cubed over 3 plus t squared over 2 plus 3t plus 7 over 6 as required. So that's 2 examples of time-dependent kinematics. In this case, we started with the acceleration, and then we integrated to find velocity and then position. And again, this is a pretty common Calculus 1 type problem. Okay, so now what if we've got velocity dependent for acceleration? Well, in that case, we use a technique known as the separation of variables. So for instance, when we have drag force, we often get velocity-dependent accelerations. So what we've got here is acceleration is 5 times v. We're going to substitute in the fact that the acceleration is dv dt. And now we're going to separate the variables. That means get everything with a v on, say, the left-hand side. To do that, we're going to divide the v down, cross-multiply the v down, leave the minus 5 where it is, and cross-multiply up the t. I've now separated the variables. I can now integrate on both sides, because this is just a velocity term, and this is just a time term. So this is a velocity integral, so we're going to be integrating from some initial velocity to a final velocity. We see the initial velocity right here is given. And that is the initial time, which is just 0, up to some final time t. Now, the dt integral is trivial. The integral of 5 dt is just 5t, so you put in the upper and lower limits. From 0 to t, and you just get minus 5t. Okay, so the right-hand side wasn't too hard. The left-hand side, integral dv over v, is ln of v, and we have to put in the upper and lower limits. So that's ln v minus ln of 0.6, but then we use the log trick. Log a minus log b is log of a over b. And now we reunite the left and right-hand side. What we do next is we raise both sides to the e, and so e undoes ln, so we end up with v over 0.6 on this side. And on this side, we end up with e to the power minus 5t. Cross-multiply the 0.6, and you're done. Now, as a plausibility argument, we notice that this means that velocity is a function of time, is a decaying exponential, which we would expect in the case of a drag force, and it starts off with its initial value, the given 0.6 meters per second, which is entirely reasonable. Okay, so that technique was the separation of variables and then subsequent integration. Now, a final technique involves when we have a position-dependent acceleration. That often happens with springs. So we know that a velocity is ds dt, and we know that acceleration is dv dt. So this equality is patently true. We can cancel off those dt's, and we'll get v dotted with dv equals a dotted with ds. And that dot is actually a vector dot product, which I hope you've encountered before. Now, once again, we'll be integrating this. Let's do that. Maybe, yeah, I guess I can fit it in here. This is the integral of v dot dv, and that's going to equal the integral of a dot ds. Now, the integral of a dot ds is once again the area. That's area. It's the area under an acceleration position graph. Now, provided v and dv are parallel to each other, then we can just drop the dot product, and this just is v dv, and v dv integrated would be v squared over 2. So in the case of one-dimensional motion, this side is integrated really easily, because v and dv are either parallel or anti-parallel. All right, let's look at a problem. Typical problem is springs. So what do we got here? So we've got a mass right of equilibrium on a spring. It's moving 1.25 meters per second as shown. Find the speed after it moves 10 centimeters further. Well, all right. So here we are. It's going to be over here, 10 centimeters further, so it'll be at 30 centimeters. Now this is a simple enough problem to do by energy conservation. It's just a physics 11 problem, but let's try and do it by integration using calculus. We know that the spring force, which is going to be slowing this down, is going to act to the left because we're beyond the equilibrium point, so the spring is stretched. And spring force is K times the extension S, and the K constant is given here. K is in units of newtons per meter, you may recall from physics 11. Okay, now clearly the displacement is to the right, so these two vectors are opposite to each other. The force and acceleration are that way, the motion is this way. As a result, the dot product is negative. Now, the acceleration will be the force over mass, so this is going to be K over mass times S ds. And the minus sign just reflects the fact that these two things are opposite to each other. Okay? So here's an expression for A dot ds. So I know that V dot dv equals A dot ds. Oh, that's horrible. Let's try that again. Clean that up. Okay, so one more time. That's probably changed. Yes. Silly thing. Okay, so V dv is going to equal ADS Okay, now this is a velocity integral, so we're going to be integrating from an initial velocity. We see that's 1.25. Final velocity is what we're looking for. And on this side, this is a position integral. Our initial position we can see is 0.2. And we're going to be integrating up to some final position, which we know is 0.3. Okay, so we put in the acceleration function. That's minus k over m, and we're going to integrate s ds, and we're doing it from 0.2 up to 0.3. Okay, and on this side it's v dv, and the integral of v dv is v squared over 2, of course. And then that's going to be from 1.25 up to our unknown final speed v. Over here on this side, minus k over m. Well, the integral of s ds is just s squared over 2. And that, again, is from 0.2 up to 0.3. So this tells us that 1/2 the unknown velocity squared minus the 1.25 squared, that's the initial velocity, is minus k over m. I suppose we can put in the value for k is 35 and the mass is 8. And then this is going to be the 0.3 squared. I'll also pull out the 2, the 1/2 here, minus 0.2 squared. So this equation, let's not miss the squared here as well. This equation, when solved, will give us the correct value of velocity. We notice, though, that if we compare this, we see things like 1/2, cross-multiplying the mass here, it'd be 1/2 mv squared. That's like kinetic energy. When the mass is gone, this is 1/2 ks squared. That's just spring energy. So what we've really done here in our integration is we've just reproduced energy conservation. And if you compare the physics 11 solution here, you'll see that each of those terms is identical to what's on the previous page, subject to a little algebra rearrangement, and this is the answer that arises. Okay? So this integrating factor, v dv is ADS, this is really another way of writing mechanical energy conservation. Okay, next thing to consider, this is really still review in nature, erratic motion, just piecewise functions. So here we've got, this is acceleration versus time. We see the acceleration but from time 0 to time 8 is decreasing linearly, not constant, and then after there's no acceleration. We're asked to find the velocity as a function of time. Okay, so we remember that acceleration is dv dt. So if we cross multiply, we get dv is a dt. This side's a time integral. We start at time 0, and we integrate up to time t. This side's a velocity integral. The object starts at rest, and we integrate up to some velocity v. Okay, so a dv integral is really simple. That's just v. Then you put in the upper lower limits and subtract, so that's easy enough. Our acceleration function, we've got to substitute that in here now. We see it's 4 minus a half t. So this is going to be 4t, and this will be minus t squared over 4. Okay, so let's clean that up a little bit. That's 4t minus t squared over 4. And so rearranging, we get, well, 4t minus t squared over 4. By the time you bring the 0 over, that doesn't change anything. And now that works up to t is 0 to 8. So at 8 seconds, you can put in 8 for the time and see what you get. 4 eighths is 32. This is 64 over 4. That's 16. So 32 minus 16 is just 16. Now for the second part of the motion, then, you'd set up the same integral, dv. So this is now for part 2 of the erratic motion here. For part 2, and this is going to be a dt again. Now you're starting now, this second part starts at 8 seconds, and it starts at a velocity of 16 that we just worked out here. Now this turns out to be a trivial integral because the acceleration is just 0, so there's no change in the velocity. The dv just gives us v, and then we put in v minus 16 equals 0. So the velocity equals 16 meters per second. Constant, that makes sense because it's 0 acceleration afterwards. So our overall answer as a piecewise function then is 4t minus t squared over 4 on the interval 0, 8. And then it's just 16 on the interval 8 up to infinity from there on in. Okay, now we can step up to 3 dimensions here, and the same rules apply. If we work in Cartesian coordinates in ijk, then the good news is we can just piecewise differentiate, meaning, or we can component-wise differentiate. To find, if you know the x, y, z position, you can find the x, y, z velocity just by differentiating the components. So the x velocity will be just the derivative of the x position, and so on, and say like the y acceleration is just going to be the derivative of the y velocity, which is going to end up being the second derivative of the y position. So component-wise calculus works, is the basic message. So as a for instance, let's look at a position described in terms of ijk. This is sometimes called parametric equations. We're asked to describe the path and then find its velocity as a function of time and its overall speed. So describing the path just means plotting the parametric equation, and what you do there is you just pick a bunch of values of time. So here, copied into the table of values are the x, y, and z coordinates, the I, j, and k. So if we put in a time as 0, the cos of 0 is 1, and this is just 5. Putting in a time as 0, the sine of 0 is 0, so y is 0. 0 for t gives 0 for z. So we're right here on the x-axis at time 0. Okay? Picking the clever time of pi over 6, 3 pi's over 6 is pi over 2. The cos of pi over 2 is 0. Again, the clever time of pi over 6, 3 pi's over 6 is pi over 2. Side of pi over 2 is 1. And then z is just half the time value. Half of pi over 6 is is pi over 12. So the z's increased a little bit. That's this point right here. So now, if we, the next key time will be, say, pi over 3. 3 pi's over 3 is pi. Cos of pi is -1. 3 pi's over 3 is pi. Sine of pi is 0. And then a half of pi over 3 is pi over 6. So you see that over time, the z value is increasing. But what's happening with the x and y is they're just circling around. So we're now way over here above the negative x-axis. Let's try and do this justice here if we can. We'll go through like that. Yeah, so we're now directly above the negative x-axis. Project that down. Y is 0 there, and our z value has now increased, right? It was a little pi over 12, it's now pi over 6. So as time goes on, we're going to circle here, and we're going to rise and rise and rise up above the xy plane. This is a spiral. Okay, so we're really moving in a circle of radius 5 here, but as we trace out the circle, our z component increases. All right, so we want to find the velocity as a function of time. Well, for the velocity, we're just going to differentiate the position component-wise. So we just differentiate this to get the x velocity. So we've got to differentiate cos 3t. Well, maybe I'll write that out. So it's the ddt of, well, I can do it this way, 5 cos 3t, 5 sine 3t, and then a half t. And then I'll just write this like that. So that's another way of writing the ijk. This is like a vector notation. So 5 comes out of the derivative. The derivative of cos 3t is sine 3t. But then you have to multiply by the derivative of the argument. You get times 3. Here we go, the ddt of 5 sine 3t, you pull out the 5, derivative of sine is cosine, but then again you have to multiply by the derivative of the argument, that gives you times 3, and then the derivative of t over 2 is just a half. So that is the 3 components of velocity, x velocity, y velocity, z velocity. So this works out to be minus 15 sine 3t, that's the I component, I'll just switch back to ijk, plus 15 cos 3t, that's the j component, plus 0.5 in the k direction. So those are the 3 components of velocity. So we've found the vector velocity. Now the speed, what's that? Well, the speed is the length of the velocity vector. And in 3 dimensions, we find the length of the velocity vector by using 3-dimensional Pythagoras. So we're going to square the x, the y, and the z velocities. We're going to square them, add them, and root them. This is the 3-dimensional generalization of Pythagoras. So that means we've got minus 15 squared. Well, the minus is gravy. That disappears. So we get 15 squared sine squared. 15 squared is 225. That's from the x velocity. The y velocity is going to be 15 squared cos squared. And then when we square the z, it's square root of a half. That's just a quarter. And then, of course, we still have to root all of this. Now, we could factor out the 225 here, because both of these have 225. And then that gives us sine squared plus cos squared. I don't even need the 3t. It doesn't matter what the 3t is as long as it's the same, because sine squared plus cos squared is just 1. And that means that underneath the square root, we've got just 225 plus 0.25. It's the root of 225.25. And that's going to be a tiny bit more than 15. 15.0, maybe 0.02 or something like that. Let's just work it out. So there you see it, it's 15.008. So it's about 15.01. And then that'll be, do we have units here or not? No units specified. So that's units per second for the speed. So if it was SI, it would be meters per second. If it was in imperial units, it would be feet per second. Okay, so you've probably done this in your Cal 3 course. This is just component-wise differentiation to find velocity. And then you could do another derivative to find the acceleration vector in 3 dimensions. Here's another problem in Cartesian coordinates, the free fall problem, the familiar projectile motion. The acceleration, you just have downwards g. We'll call this the y-axis and this the x-axis. So a downwards gravitational force is in the negative j direction. So there's our gravitational acceleration. And we want to find velocity as a function of time and position as a function of time. Now, we've done this problem to death, but we're going to do it very efficiently here because we can treat the components all at the same time, and we don't need to separate them out like we've done before. So for instance, we know that acceleration is dv dt, or cross multiplying, we know that dv is a dt. And then we're going to integrate from an initial velocity to a final velocity. And then we're going to integrate this side, this is a time integral, from the initial time, well, that's just going to be 0, to the final time, t. Let's just clean that up a tiny bit. All right, and I have to change the defaults. That's very irritating. Okay, from an initial time of 0. All right, so here the acceleration is 0I, gravitational downwards, g downwards, and then nothing in the k direction. So that's the acceleration function dt, so that's pretty easy to integrate. And then we're just integrating it from 0 up to t. Well, you get nothing from the x integration or the z integration. You just get negative gt in the j direction. On this side, the integral dv is just v, and then you put in the upper and lower limits, so that's going to give you v minus v naught. But of course, v naught can be broken into components. It's going to be cos theta I and sine theta j. So it's v naught cos, what was that? Yes, so cos theta I plus v naught sine theta j. Just try and do that neatly for enhanced legibility. So we can now solve for the velocity as a function of time. So this is going to come over to this side. So the only I component is this one. It's just v naught cos theta I. And then in the j direction, it is v naught sine theta minus gt. And then there's nothing in the k direction. Now, if you look at it, this tells us that we have constant x velocity, and it's v cos theta, and then the y velocity is changing at a rate of downwards g. This is, of course, exactly what we would have said in Physics 12. Now, we can integrate one more time because dr is v dt, and we can integrate from our initial time, which is 0. And this side, this is an r integral, so we're going to integrate from our initial position to our final position, r. Now, the integral of dr is trivial. That's just r, and then you put in the upper and lower limits. So this is just r minus r naught, the initial position. This side, we now have to work a little bit more than we did before because there are lots of terms here. There's going to be the v naught cos theta I. That's just constant. Then we're going to have v naught sine theta minus gt in the j direction. But all of this is going to get integrated now dt, because it's velocity dt. So this is v dt. So the constant term gets pulled out in front of the integral. But then you get integral dt, which is just t. So it's v naught cos theta times t in the I direction. Then in the j direction, there's two integrals to do. V naught sine theta dt. That just gets pulled out. So that just ends up V naught sine theta t. And then the gt, the g gets pulled out. You've got to do integral t. That works out to t squared over 2. And then that is all in the j direction. Now, if you look at that, once again, that is just physics 12, because this is like VIT plus 1/2 AT squared, where the acceleration is downwards g, and it says in the x direction, because the velocity is constant, the distance in the x direction is just velocity times time. I suppose the last thing we could do is we could put in the fact that the initial position in this case is simply nothing in the I direction, and it's y naught in the j direction. And if we wanted to solve for the vector r as a function of time, it just works out to be v naught cos theta t in the I direction. Bringing, this is minus r naught, so when you bring it over to the other side, it's positive y naught. And then here's our expression for the position of the object as a function of time. All right, so it's the projectile problem, but it's the projectile problem solved very efficiently in just a few lines. Okay, and we've got the velocity and position as the object as a function of time. So here's a problem now for you to try. So here's your velocity as a function of time. Stop the movie, try and work out the acceleration and the position based on this, and then play it and check my answer if you like. So you could pause the movie and then try it on your own. Okay, so hopefully you had a chance to give this a try now. Let's look at the solution. The acceleration, of course, will just be the derivative of velocity. So differentiating, you just get nothing I minus 3j and then nothing k. So that's the acceleration function. For the position function, you're going to have to integrate. So dr is v dt. You're going to be integrating from an initial time, which is 0, and you're going to be integrating from an initial position. That also is 0, 0, 0, up to r and t. So this ends up being r minus the initial position, which is just a 0 vector. And you've got to integrate your velocity. That's going to give you 4t I minus 3t squared over 2j plus 2t in the k direction. And because r naught's the 0 vector, you just end up with exactly this term here as your position as a function of time. Okay, so this once again is just time-dependent, three-dimensional Cartesian kinematics. Fairly straightforward Cal 1 or Cal 3 problem. And that's the end of our first class preparation video. So fill in these notes. You can attempt the assignment problems, and then we'll take it up from there on when we meet in class on Friday.